Alright, section 8.3, we are going to be graphing, and first we'll actually be evaluating and then graphing piecewise functions, and then graphing some common functions along with some shifting and reflecting. So we have a lot in this section, so I'm hoping that by watching the video first we can do some things in class, and that'll actually help a very, very full section here. So number one, g of x is what we call a piecewise function. So it's defined in two different pieces. It's defined to be this function x minus 2 if x is greater than or, less than or equal to negative 3. So it's the x minus 2 when x is less than or equal to 3. And it's this negative 2x plus 8 if x is greater than 3. So basically it is a function that is defined in two different rules. The first rule, when x's are less than or equal to 3, so this tells us when to use this rule. And then the second rule tells us it is the line, negative 2x plus 8, both of these are lines, and we use that rule if the x values are greater than 3. So the first question, we'll do a part A. We simply want to be able to evaluate at specified values. So if I said evaluate g of 1, so because 1 is less than or equal to 3, so this is not something that you would have to show me, but we could say because 1 is less than or equal to 3, that tells us to plug into the top rule. So this tells us to plug into the x minus 2 rule. So in for x is 1, so 1 minus 2, we get negative 1. Okay, part B, let's do another value. Let's evaluate g of 4. So the first thing we look at here is realizing that because 4 is greater than 3, so because 4 is greater than 3, we plug into this second rule. So this is going to tell us we plug into negative 2 times x, which is 4, plus 8. So of course that is negative 8 plus 8, and that comes out to be 0. Okay, so initially this is the idea of a piecewise function, just a function defined in different pieces that we plug in differently depending on which type of x value we're given. So number 2, we have an f of x that again is some sort of a line, and this is for x's that are less than or equal to negative 2. And then the rule changes to 2x squared plus 3 when the x's are greater than the negative 2. Alright, so for part A, let's evaluate f of 1. Okay, again, the first thing I want to look at is because 1 is greater than negative 2, okay, that is going to tell me to plug into the second rule. So 2 times 1 squared plus 3, well, 1 squared is 1, so I'd end up with 2 plus 3, which would equal 5. Part B, let's do another one. Let's evaluate f of negative 2. Okay, so I look at that x value and I observe that because negative 2, well, it's not greater than negative 2, and it's not less than negative 2, but it is or equal to. So this or equal to line means it does satisfy that first condition. So negative 2 is less than or equal to negative 2. That tells me to plug into the first rule. So negative 1/2 times in for x is negative 2 plus 1. So these 2's we could reduce, and I'm left with negative times negative. 1's is positive 1, and 1 plus 1 is 2. Alright, last one here. So this one's defined in 3 different rules. So it is defined as negative 2x plus 4, this line when x is less than 1. It's defined actually for just the one single value at x equals 1. It's defined to simply equal 4. And then for any values that are larger than 1, so when x is greater than 1, it's this parabola, the x squared plus 1. So let's look at a few values. So for part A, let's evaluate h of negative 5. Okay, again here, because negative 5, I look at my conditions, it is less than 1. That's the rule that's satisfied. That tells me to plug into the negative 2 times negative 5 plus 4. So I have 10 plus 4, so 14. Okay. Part B, let's evaluate h of 1. Okay, well this time 1 is not less than 1, it's not greater than 1, it is equal to 1. So obviously 1 is equal to 1. Well, that tells me that at this one single value of x equals 1, the output is simply defined to equal 4. And lastly, part C, let's evaluate something like h of 3. Okay, again here, we look at the inequality that is satisfied to decide what to sub into. So because 3 is bigger than 1, that tells me to sub into the bottom rule. So 3 squared plus 1 is 9 plus 1, which is 10. So initially we just want to know how to evaluate these piecewise. Alright, so after being able to evaluate functions at specified values, we now want to move on to graphing these piecewise functions. So essentially we have a function that gets defined in two different pieces. So this is the same number 1 we saw before. So we have one function for values of x less than or equal to 3. So we have one portion that will be for x's less than or equal to 3. And then we have another portion that will be for values that are greater than 3. And maybe I'll use a different color over here, so I'll change it to a black color here. Alright, so as we initially look at these values, okay, so the first thing I see for values that are less than or equal to 3 is this is definitely a line. It's the line y, or g of x, equals x minus 2. Okay, so the first thing is to realize we're really looking at the line y equals x minus 2 on this region. So I would just start by plotting some points that satisfy this criteria. You technically only need 2 points to graph a line, but picking values that are less than or equal to 3, so maybe I sub in, x equals 1, or maybe I sub in x equals 2. So if I sub in 1, I get 1 minus 2, which is negative 1. If I sub in 2, I get 2 minus 2, which is 0. If I sub in 3, I get 3 minus 2, which is 1. And that's where I'd want to stop, because this is the line only for x values less than or equal to 3. So we could start that graph. We could say, all right, I have the point 1, negative 1, 2, 0, 3, 1, and I can see this line here. It has a slope of 1, but I just need to be careful that I don't go to the right of that. It has to stop at 3, but it should continue here to the left. So it goes up until that point, but it should also be defined to be this line for all values that are less than or equal to, but for all these values less than the 3. So it does continue there. We just had a few points, and we want to be real clear what happens at this cutoff point where it is defined. So make sure that when you graph that point, you're really showing it with a nice solid filled in circle there. All right, now let's look at what happens for x values that are greater than 3. So for x values greater than 3, we're really looking at the line y equals negative 2x plus 8. Now, even though 3 is really defined over on this first branch, I need to figure out right where this second portion of the graph is going to start. So we always graph what I call the cutoff points. We always graph it on both. So when I sub 3 into this equation, I'd have negative 2 times 3 is negative 6, plus 8 would be 2. But technically this point does not exist here because it was defined over here on this first branch. So when I graph this, I'm going to have to do so with an open circle. So at the point 3, 2, this function is technically not defined there, but that's exactly where the graph will start. So I want to be really clear about that. Now I want to pick values that are greater than 3. So maybe something like 4. Negative 2 times 4 is negative 8 plus 8 is 0. So I get 4, 0. And I can also see that from my slope. My slope was down 2 over 1. And I could continue to count down 2 over 1. That's the same value I would get if I subbed in 5. Negative 2 times 5 is negative 10 plus 8 is negative 2. So here I am at 5, negative 2. And I could keep going down 2 over 1, down 2 over 1. So we can continue in that way to get more points on the line. Just like on the first graph, once we start to recognize that the slope is up 1 over 1, we could also have went down 1 into the left 1 in order to get more points on that first graph as well. So here's our first piecewise function graph. The graph in blue for values less than or equal to 3, and then the graph in black for values greater than 3. All right, let's look at another one here. Let's take a look at number 2. So number 2 again. Okay, I sometimes had issues with this camera, so I noticed it had stopped, so I just kind of did a little whiteout over what I had done, and this should pick us right back up where I left off. So for x less than or equal to negative 2, we have this first rule. So we're using the rule y equals this negative 1/2 x plus 1 equation that we're using. So this is for the x values less than or equal to 2. So picking values less than or equal to 2, maybe I pick something like negative 4. Negative 4 times negative 2 would be 2, and then 2 plus 1 would be 3. I could pick negative 3. I'm going to end up with maybe a little bit not as nice of a value here if I start with negative 3. That's okay. Negative 3 times negative 1/2, so that would be positive 3/2. So that's positive 1 1/2 plus 1 would be positive 2 1/2. So that was at, again, I just had a little issue there, so I'm sorry if this video is a little choppy for you. So at negative 3 we had, the positive 1 1/2 plus 1 give us 2 1/2. Okay, at negative 2 times negative 1/2 would be 1, and then 1 plus 1 would be 2. And this is where the function ends, but this is where it is defined. So when I graph this point, because this is where the or equal to line is, I want to be real clear at what happens at those cutoff points. All right, so let's plot some of these points. Negative 4, 3, 1, 2, 3. Negative 3 up 2 1/2, so not great, but still okay, just a little harder to graph that. And then at negative 2, I end at 2, but with a nice, very clear, kind of solid circle there. And if I want to continue my slope, I just have to be careful that I don't go down 1 over 2, but instead I go up 1 and to the left 2. So up 1 and to the left 2, up 1 and to the left 2. so this line is defined for all values less than or equal to -2. All right, now for the values of x that are greater than -2. Okay, so for the values of x greater than -2, we're looking at this U-shaped parabola graph, which we've started to see a little bit more and more. Y equals 2x squared. At this point, you should at least recognize it's not linear. So 2x squared plus 3. So I do want to start right at this point of -2. And when I sub in -2, -2 times -2 is 4, times -2 is -8, plus 3 is -5. So -2 times -2 is 4. Oh, I'm sorry. Let's do that thought again. -2 times -2 is 4, times 2 was 8. I think I said times -2. Times this 2 was 8, plus 3. This should be 11. At least I caught myself there. So at -2, we're at 11. Okay, but this should be graphed, this -2, 11. Okay, this is really not defined there because -2 is defined over here at 2, but this is where the second part of the graph will pick up immediately after that point. So we graph it with an open circle. So at -2, and then up here at 11, if we continued our graph here, we would have an open circle. All right, so let's plot some more values greater than -2. So let's go to -1. So -1 squared would be 1, times 2 would be 2, plus 3 would be 5. So at -1, I'm at 5. So -1, I'm here at 5. Okay, let's graph 0. 0 plus 3, that's nice. That's just 3. Right there. And until I get my kind of U-shaped graph, I have to really keep going here. So let's graph 1. This would be 2 plus 3, and this would be 5. So this is a good sign. At 1, I'm at 5. So I'm starting to see this symmetry. So I've likely made the turn now on my parabola. Let's just do one more point to be sure. 2 times 2 is 4, times 2 is 8, plus 3 is 11. So at 2, I would be up here at 11. So this is kind of a pretty narrow parabola here. So we had a few points on that parabola that we just found, as well as that open circle at -2, 11. All right, number 3. We have the 3 different pieces on this one. So this one's a little bit different, maybe than the first 2. So for x is less than 1, okay, that's where we have the graph y equals -2x plus 4. So, I'd probably graph a few points that are less than 1. So maybe -1, 0. So at -1, this would now be 2, plus 4 would be 6. At 0, this would be 0, plus 4 would be 4. And then when I get to 1 itself, -2 plus 4 would be 2. But I need to graph this one with an open circle because there is no or equal to line here. So technically 1 is not defined at 2, but the graph goes all the way right up until that point. So at -1, 6, I had a point. At 0, 4, I had a point. And at 1, 2 is where the graph ends, but with an open circle. Again, observing my slope is down 2 over 1. I can go up 2, left 1, up 2, left 1, up 2, left 1, and just kind of use that to get a little bit more accurate of a graph. All right. Now, right at 1, so for x equals 1, we have the point, the rule is y equals 4. So this is just the one point. At 1, the y coordinate is 4. So this is where this point is defined, and so we graph it with a very clear filled in circle. So at 1, 4, that is where this point is defined. And then lastly, for values that are x greater than 1, we're using this last rule, which again, we should at least recognize that it's not linear. Hopefully starting to recognize that that's that parabola that we've seen quite a bit. So I do want to figure out what's happening at 1. So when I sub in 1, I get 1 plus 1, which is 2. But this is not where this point is defined, so I need to make sure I graph that with an open circle. So at the point 1, 2, looks like that's right on top of the open circle that I had from this left branch of the graph. And now we'll just plug in a few points greater than the 1. If I plug in 2, I get 4 plus 1, which is 5. So at 2, I'm at 5. And if I keep going here, if I'm at 3, I get 9 plus 1, which is 10. So at 3, I'm at 10. And so, it's going to be kind of hard to draw that this is actually kind of this U-shaped graph. It's going to look a little bit linear because it's just so kind of steep right here. But it's just kind of a portion of that U-shaped graph, that parabola. Alright, so the next portion of this section are common graphs that we've been talking about over the last couple of days that I do want you to know. So 8.1, we spent a lot of time talking about linear functions. So this is the graph of just f of x equals x, or y equals x. Our U-shaped graph, we've been working with that over the last section or so. And that you should start to recognize as being your common parabola, f of x equals x squared. The graph that looks like half of a parabola turned on its side, okay, we've also seen this one. We've plotted some points for this one in previous sections. So this is our square root of x function. And the last one, this V-shaped graph, is kind of the last one that I want you to be able to recognize, and that was our absolute value of x. So at some point, spent a ton of time on lines, and we've also graphed all of these by just plotting points back in the previous 8.2 section. So now we're going to do some graphing and start to make some observations that we've already started to make in the previous sections, but we're going to kind of formalize this. So let's start. Number 1, again, let's graph f of x equals x squared to start. Okay, so we've done quite a bit of f of x equals x squared. Certainly, if you want to make a table of values, you certainly can do so. We've done this one before, so I'm going to just kind of quickly write up some values. Squaring each of those values, we get a quick table. So at 0, we're at 0. Negative 1 and 1, we're at 1. Negative 2 and at 2, we're at 4. And if I kept going at 3, we'd square to get 9, and negative 3 squared would also be 9. So this is the basic original f of x equals x squared graph that we need to just kind of know its basic shape at this point. Okay, so this is our f of x equals x squared graph. Okay, so let's also include on this graph, suppose we have g of x equals x squared minus 6. So if I wanted to, again, make a table of values, so let's say I have my x and my g of x here. So if I wanted to start with the same list of values, that's fine. Okay, this time we square, So negative 2 squared is 4, and then subtract 6. So 4 minus 6 is negative 2. This would be squared 1 minus 6 is negative 5. 0 minus 6 is negative 6. And again, 1 minus 6 is negative 5, and 2 squared is 4 minus 6 is negative 2. So if I plot these points, at 0 I'm at negative 6. At both 1 and negative 1 I'm at negative 5. And at both 2 and negative 2 I am at negative 2. So 2, negative 2, and negative 2, negative 2. And we could keep going. Sorry, my graph was cut off there. If we wanted to do 3, that would be 9 minus 6 would be 3. So at 3, we would be here at 3. And by symmetry, that would tell us at negative 3, we'd also be at 3. So we could keep going if we wanted to, but that certainly is enough to see what is happening with this g of x graph. Okay, so we can see our g of x here at x squared minus 6. So we've seen a couple of these over the last day or so, and what we've seen is when you have an original function and you add or subtract a number outside of that, if you add it, the graph is shifted up. When you subtract it, the graph is shifted down by that number of units. So if you have some function and you have added or subtracted a number, that is going to shift f of x either up by c units or down by c units. Sorry, keep sliding this off the screen. So the positive would tell you to go up c units, and if it's negative or minus c, then you would go down c units. Alright, so let's look at number 2 here. So let's look at another example. So number 2, suppose I have the original function f of x equals the absolute value of x. And again, we've graphed this one before if you want to make a table of values, but we've done this in earlier sections, x and f of x. Again, if I started with just from negative 2 to 2, if I take the absolute value, I get that positive result back. So at 0, I'm at 0, negative 1 and 1, I'm at 1, 2 and negative 2, I'm at 2, and I could continue. At 3 and negative 3, I'm at 3, and so on. Alright, so here's my graph, and I'm seeing this basic V-shaped graph that we have to just start to recognize, but there it is. Okay, so here is my, this is my f of x equals absolute value of x. So now let's graph another one here. So let's graph g of x equals the absolute value of x plus 2. G of x equals absolute value of x plus 2. Alright, so let's make a table of values, and we've seen some of these before. So this is not the first time we've done this. So let's say I start with my same values, and then we'll see what we have. So the same original starting points. Here, absolute value of negative 2 plus 2 must be done first, and that becomes absolute value of 0, which is 0. If I sub in negative 1 plus 2 would be 1, and absolute value of 1 is 1. If I sub in 0, I get absolute value of 0 plus 2 is 2, and its absolute value is 2. If I sub in 1, I get absolute value of 3, which is 3. If I sub in 2, I get absolute value of 4, which is 4. So at negative 2, I'm at 0. Negative 1, I'm at 1. At 0, I'm at 2. At 1, I'm at 3. 2, I'm at 4. So I'm getting a whole lot of points here, and I can really kind of see what's happening on this right-hand side. It's going to continue in that way. But I don't think I have enough to know. I mean, does it just continue down here? So this sort of calls out for us to plot a few more points that are to the left of -2. So we're going to continue with our table of values here, but this time I'm going to pick some values that are less than -2. So something like -3. -3 plus 2 is -1. An absolute value of -1 is 1. So at -3, I'm up at 1. So here I'm starting to see the early beginnings of that V-shaped symmetry resulting. Let's do a couple more just to be sure. -4 plus 2 is -2, and when I take its absolute value, I get 2. So at -4, I'm at 2, and it's pretty clear now. I'll throw one more value in. -5 plus 2 is absolute value -3, which is 3. Okay, so here we are at -5, we're at 3. So I'm getting the left-hand branch of this absolute value function. So this is my g of x, which is equal to the absolute value of x plus 2. So as we saw with some examples last time in class as well, if the number is added or subtracted inside of the original function, so this is the absolute value function, this plus 2 is inside of the function. So if the number is added or subtracted inside the function, it moves it horizontally, and the result we saw from these values is it kind of moves it in the opposite direction maybe of what we would hope. So if this was an x plus 2, it took this original graph and it moved the whole thing to the left 2. So what we see is if it is a plus c inside the function, okay, that's like what we had here, a plus 2, it actually moved our graph left that c units. And in the other situation, if it had been a minus 2, it would have moved us to the right, again, whatever that c units would be. So it's all about if it's inside or outside the function. If it's outside the function, it moves up or down, kind of in the way you would want it to. If it's positive, up, and if it's a minus, down. If it is inside of the original function, that is the horizontal movement that's kind of opposite maybe of what we'd hope. But the plus 2, that's actually what moves us to the left 2. Had this been a minus 2, it would have moved the original graph to the right 2. Okay, so this is our summary of vertical and horizontal shifting. Okay, one other observation that we want to make is going to be for reflections. So let's take a look at another graph here. So on this one, let's go ahead and say that, let's start with the square root function on this one. So we've graphed the square root function here, but what we saw, if you remember, with just square root of x, square roots of negatives aren't defined, so we started at 0, and square root of 0 is 0. Then we go to 1, square root of 1 is 1. And although we could go to 2, without a calculator, the next nice perfect square is 4. So root 4 is 2. And again, we could keep going, but the next nice perfect square is 9, and root 9 is 3. So if you remember, and this is again a graph whose common shape you're going to just need to be able to recall now that we've seen it a few times, this is the graph that is half of a parabola turned on its side. So this is our f of x equals the square root of x. All right, so let's also graph g of x equals negative square root of x. So let's start with these same values here. So at 0, square root of 0 is 0, and the opposite of 0 is still 0. At 1, square root of 1 is still 1, with just this minus in front getting carried along, so it's minus 1. And in fact, these other values will behave the same way. At root 4, I'm at 2, with just this minus in front, so I'm at minus 2. Root 9 is 3, with a minus in front, so I'm at minus 3. So at 0, I'm at 0. At 1, I'm at -1. At 4, I'm at -2. And at 9, I'm down here at -3. So what we get on this graph, so this is my g of x, and when the minus is in front of the function, we can see that the effect is it has reflected this graph over the x-axis. So that's actually the second summary statement down here. If the minus is in front of the original function, it reflects that original function over the x-axis. Okay, now let's look at what would happen. Let's stick with the same original function on this one actually. So I'll just recopy those points, but I mean we just did them. So we liked the perfect squares, and so we plotted those points 0, 0, 1, 1, 4, 2, and 9, 3. Okay, gave us that nice right hand, gave us the nice 1/2 of a branch basically of a parabola turned on its side. So we have our square root function here. Now let's graph with it. Let's look at the difference between the one we just did versus the square root of -x. So this time the negative is inside the function. So what we want to observe here is that while it certainly is okay to plot 0, I would have the square root of 0, which is still 0, it no longer makes sense to graph 1, because that would give me the square root of, the negative is under the radical, and the square root of -1 does not exist. So this time plotting the positives doesn't make any sense because there is a negative under the radical. Instead, I want to start with the negatives, so something like -1, so that when I take the square root of the minus in the function, and then I'm subbing in -1, the opposite of -1 is 1, and square root of 1 is 1. So let's jump up to the next perfect square of 4, but using -4. Again, when we plot that, we have the minus from the function subbing in -4. The opposite of -4 is 4, and root 4 is 2. And then the last one here at -9, so we sub in the minus in the function, the -9 we're subbing in for x, the opposite of -9 is 9, and root 9 is 3. So we had 0, 0, nothing we saw on the positive x values, but for x equals -1, we were at 1. For x equals -4, we were at 2. And for x equals -9, we were at 3. So what we actually see here is this is g of x equaling the square root of -x. It was the original function f of x reflected now over the y-axis. So if the minus is inside, so under the radical or inside of whatever the function is, here it's a radical or a square root, then it's going to reflect the original graph over the y-axis. So this is our summary of the reflections. So I'll save a couple of examples here for us to talk about in class as a group, and then in class you'll also be working on some exercises together with some folks around you.